Hi everyone, welcome to my presentation. My name is King Samno, and I'm a graduate student at Utsunomiya University. Today, I'm going to present a paper entitled A Study on Adjacent Interference of LoRa. In this paper, we talk about the relation between adjacent interference of LoRa and its communication parameters, such as channel distance, bandwidth, and spreading factor. And we also discuss the solution for our research based on the results. First, I'm going to introduce LoRa technology to you. LoRa is a low-power wide area network technology based on spread spectrum modulation, and its communication distance can be up to 10 kilometers with a strong noisy resistance. LoRa is widely used in varieties of areas, especially in agriculture due to its advantages of low cost, low power consumption, long-distance communication, and thousands of device connection capability. As one of sub-gigahertz wireless communication technology, LoRa uses carrier sense to avoid interference according to Japanese regulations. If the carrier sense level is above the threshold, LoRa fails to send data and returns an error message. In our research, we are intended to construct a livestock monitoring system by using LoRa. But we found that there were a large number of errors in the data log when we used adjacent channels for transmitters. Adjacent interference leads to a serious impact of communication efficiency decline and a large-scale communication congestion when there are hundreds of transmitters. So in this paper, we aim to figure out the degree of interference between channels and its relation with different parameters to find out solutions for our research. In our experiments, we used two same transmitters set to start and stop at the same time. The two transmitters continuously sent data packets for more than 10 minutes and recorded the successful or failed transmission. At first, we tested different parameter sets selected from table 1, and the results show that there is no carrier sense detected when spreading factor is 7 or 8, and the carrier sense increases significantly when spreading factor varies from 9 to 12 in bandwidth 3. So in order to show consistent interference changing, we conducted experiments with spreading factor varying from 10 to 12 and bandwidth varying from 102 and 25 to 500 kilohertz. To measure the interference degree of adjacent channel with different distance, we tested 5 sets of channels. For example, when the two transmitters are set with the same channel 1 and channel 1, the channel distance is 0. When we set channel 1 for transmitter and channel 2 for another, the channel distance is 1. We also changed the distance between two transmitters within 100 meters to find the maximum interference distance in different conditions. Regarding to the definition of a carrier sense rate, CSR, we can calculate the carrier sense rate based on the number of successful or failed records of two transmitters as the equation. First, we analyzed the relation between CSR, bandwidth, and spreading factor. As shown in Figure 4, we found that a smaller bandwidth or bigger spreading factor leads to a higher CSR, which means it's more likely to cause adjacent interference when using a smaller bandwidth or bigger spreading factor on equal terms. Next, we measured the interference with different channel distance. Considering that the interference degree of the same channel distance may be different. For example, channel 1 and channel 2, channel 3 and channel 4, the channel distance is the same, that is 1, but the interference degree may be different. So we tested 4 channel sets of each bandwidth. The relative standard deviation under 1% demonstrated that there is a same degree of interference at the same channel distance. As shown in Figure 5, CSR decreases slightly from the same channel to adjacent channels, which means adjacent interference is as serious as co-channel interference. and CSR drops sharply when channel distance is above 2, and it nearly downs to 0 when channel distance is above 3. So we can infer that LoRa is more sensitive to interference when using a smaller bandwidth or bigger spreading factor, and we can significantly reduce interference by using channel with a distance above 3. In the end, we also measured the interference distance under different bandwidth and spreading factor when using adjacent channels. As shown in Figure 6, a smaller bandwidth or bigger spreading factor leads to a longer interference distance. So it's available to make sure that the distance between nodes using adjacent channels is above 40 meters to avoid interference. Come back to our research. There are hundreds of cows on the farm, and it will lead to a serious interference when grazing. According to our result, we can group livestock at separate sections and allocate non-adjacent channels to avoid interference. As shown in Figure 7, we can group livestock at 5 sections and divide 15 channels to 5 sections with non-adjacent channels. The maximum duration of communication for one payload is 5 seconds when using LoRa. Taking the slow movement of cows into account, we can set 60 transmitters using the same channels to send data one by one during 5 minutes. It implies that we can monitor 900 cows with 15 channels in this model. Of course, it's impossible to evaluate the real interference condition with only 2 transmitters. We will take a first step to use more transmitters to simulate an actual condition and analyze the interference in complex situations in the future. That's it. Thank you.